This is another problem on a different kind of water slide, and this used to be, or still is, a problem in a different edition of our physics book, and I just put it in here because I like the problem because there's some physics involved. But since you don't find it in your book, it wasn't assigned. Okay, so don't freak out that, oh gosh, I've never seen this problem. So anyway, here's what the problem reads in this other edition of our book. A person starts from rest at the top of a large frictionless spherical surface and slides into the water below. See the drawing. At what angle does the person leave the surface? Hint: when the person leaves the surface, the normal force is 0. As I read this here, there are no numbers given. That's the first thing that's kind of interesting. One of the things that's kind of interesting. And then we're supposed to come up with this angle theta here. So theta equals question mark. But apparently it's independent of the radius r, and interestingly enough, if we have this water slide here or on the moon, it doesn't matter what gravity we have, all that actually somehow divides out. It doesn't depend on any of these. We'll be using these here. But anyway, let's get started. This chip, let's see what is given. The mass is not given. Apparently we don't need it. Gravity is implied. The height is kind of given here. The difference in height, we'll calculate that in just a moment, but it depends only on r. So perhaps it's given, perhaps it's not. V0 is pretty much the only thing that is given, because she starts from rest up here. Okay, as I said, maybe we have this here, we'll see. Okay, the problem should be about energy, and so that means at the top versus the bottom. And actually, I don't think I'm going to write the bottom. I'm just going to write leaving the surface instead. So at the top, and then versus leaves the surface, because that's what they're asking for. So at the very top, we have potential energy, and that equals then, of course, kinetic energy, where she leaves the surface. And of course, it says frictionless, yep. And then we could say that it's plus potential energy. I'm going to write this down here for a moment. But here, again, I have a choice of if I use my 0 line for the potential energy down here, or if I use it here where she leaves the surface. Either way, I just like to do this one here, because then there's one thing less that I have to calculate, and I put that a little bit too low here. Oops. There we go. It's a little better. So there's my 0 potential energy line, which means that this is just PE plus PE equals KE. So to begin with, she has her mass times gravity times height, and this is the height here from here to here, height h, and that equals 1/2 mass times velocity squared. Of course, we can see that the mass divides out. Okay, well, here's what the height is. The height is the distance r, the radius, minus this distance here. And this distance here I can kind of calculate. Notice that this part here is the adjacent to this angle, and that means I'm going to deal with the cosine. I personally prefer always to measure from the horizontal x-axis, but for this kind of problem, or for a pendulum problem, those kinds of things where it's more convenient to deal with the angles from the vertical, I guess I let it slide that I measure from the vertical, and my cosine actually is on the vertical because it's adjacent to the angle. So what I have here is this piece here is r times the cosine of the angle. So gravity times, gravity times the total r minus r cosine of the angle, because this piece here is radius times the cosine of the angle, and then I subtract this piece here from the total radius, and that gives me then the h. Okay, and that equals 1/2 v squared, and maybe I want to call it vf squared, and there's also vf. Okay, in this equation here, there's a lot of stuff in here. There's the g, which we have implied. There's the r that they don't give to us, so that's an unknown. There's the theta that we're supposed to come up with, and there's the vf that with which he leaves the slide, which we don't know either. So, wow, we have all these unknowns here, which means there must be more to it. And that comes in where she leaves the slide right here, where they say then here, just as she leaves the surface, the normal force is 0. So that means that here the only force that is acting on her is her weight, mass times gravity. Now, as she's sliding around here, they say it's a spherical surface. That also means that we have a centripetal acceleration on her, and that centripetal acceleration is pointing this way. And if I draw this a little bit better, then it looks like this, and that would be now actually the component of the weight in this direction here. Now there would be also a normal force pointing the other direction. However, they say here's where she leaves the surface, and that means that the normal force is 0, and that's why the only force that is kind of pushing her in still at this point here is this component of the weight. It looks a little bit weird to do it this way here, because it looks like gravity is pointing sideways at this component rather than down, but what is happening is that this component of the weight actually tries to push her into the surface and therefore supplies a centripetal force, while the other component in this direction here, of course, has been accelerating her tangentially to the slide. So that's why I can split it up into two components. This one here accelerates her, and this one here supplies the centripetal acceleration or centripetal force. Okay, there is also an angle between these two, and that angle you can see is the same as this one over here. So that's the same theta, and when I want to calculate this one here, I also use the cosine, because this one here is adjacent to that angle theta. I take that back, what I just pointed out. What I meant to say is, let me actually take a little bit off here, is that a component, of course, the components, of course, are the ones that are perpendicular to each other, and that means that this one here is adjacent to the angle, and this one here being the hypotenuse in this triangle. So that means that at this point here I have a centripetal force which is completely supplied by that component of the that component of the weight. So this one here is the centripetal force supplied by the weight, and that equals mass times acceleration, and for centripetal force, that is centripetal acceleration, that is v squared over r respectively. Of course, we're looking here at vf.